Hello, everyone. So today we're presenting SkyDiscover, which is the automated AI-driven scientific and algorithmic discovery. So we're all PhD students from the UCB Berkeley Sky Computing Lab. So LLM-driven optimization has been a while. So basically, in that setup, you have some sort of agents as the generator, generating candidate solutions for being evaluated. So there are many problems that people are focusing right now. So let's say like those math problems, system performance optimization problems, algorithm code generations like kernels, and prompt optimization, etc. So there are many recent work, for example, like font search have been like a work from Google that talks about how do you do mathematical discoveries from program search with large language models, Alpha Evolve or Open Evolve, and like JAPA, Shinkai Evolve, etc. So those kind of like tools are basically using LMs to generate like novel solutions for all kinds of tasks. And in this kind of setup, you're having like evolutionary search for LM-driven optimizations where you have some sort of generators, let's say LLMs, and then you have a program database that store all of your past solutions, and then you learn how to sample from it to propose it by the next candidates. So in this setup, the strategy becomes how do you select and present prior experiences for better generation? So for example, what kind of candidate solutions are selected, and how do we present them to the LLM so that it can better generate the next one? So some example that we showed before is like, for example, OpenEvolve would mutate some like top and diverse solutions. Shinkai Evolve maybe having some way to do like novelty rejection. So you will reject like less novel solutions or mutate top and diverse candidates. And something like JAPA would do like Pareto selections and mutate or recombine just like different ideas together to basically generate a new one. So all kinds of setup for this kind of like evolutionary search for ARM-driven optimizations have many configuration knobs. So for example, as I talk about OpenEvolve, you need to decide like how do you set this like exploration exploitation ratio? How do you set the number of islands, migration ratios, and similar to Shinkai Evolve. So it's like this kind of like island and number of inspirations you need to set, and also like novelty generator, etc. And even for like simpler algorithms like bean search, you need to sort of like decide what kind of context you want to select by this parameter knobs. And of course, the challenges here, we've seen so many frameworks have independently implement similar core components like memory management, selection, generation, and then evaluation. And basically, researchers typically need to repeatedly review similar infrastructure. So this kind of fragmentation makes it super difficult to reuse ideas and extend prior works. And also in terms of like evaluation and monitoring. So when these algorithms are coming out, so evaluation is oftentimes inconsistent with different benchmarks and reporting metrics. And we'll also want to be able to monitor the optimization process as human in the loop. So we want to be able to answer what kind of like structure or pipeline works the best, what benchmarks do we evaluate on, and how does the evolution go? And lastly, many systems are just tightly coupled to one of the algorithmic worldview. So for example, previously I give some examples of like, okay, you need to have this island structure of how do you select the candidate solutions for generating better next one. And then like Pareto, frontier, curve, like different algorithms have different structure. And throughout this optimization stages, this kind of fixed algorithms with hand-tuned parameters typically does not work well. So maybe you see some good initial progress at, let's say, the first 50 iterations, but then it will quickly stagnate at the later iterations as well. So even cloud code, when you run it from like just naively run it, sometimes it can get lazy. It will tell you like, okay, I've already reached the best solution that I can get. And then it will waste a lot of like iteration budgets and also tokens in terms of like exploring this kind of novel solutions. So we basically build SkyDiscover to be able to do adaptive and flexible our AI-driven discovery. So we want to address these three challenges that we talked about before to have like modular components that are basically reusable across different algorithms and like different pipelines. So for example, evaluators and context management. And we also want to do adaptive optimization. So we want to be able to monitor the progress and stagnation of your optimization process and even enable AI to also optimize its own optimization process. And we want to focus on real world end-to-end problems. So let's say this kind of like we have supported 200 plus problems, including those like math problems, system performance optimization problems, competitive programming problems, and also a bunch of like software engineering tasks in hardware as well. So we want to not only just like target those problems, but also we want to focus on a full stack real world system optimization task beyond toy benchmarks. So here's the entire loops of what we have in the framework. So basically, we're having some sort of like context builder that tells you what kind of problem context you have. And the agents are basically any sort of LLMs calls where any sort of like agent scaffolds that you have. So let's say clock codes or codecs that are interacting with some sort of environments. And then the output can be any sort of output. So it can be like text output, it can be code, it can be image, etc. And being evaluated with some scoring functions. And also, along with the scores that you get, you can have some metadata feedback. And basically, the left-hand side of this context builder and solution selector parts are the key parts of here is like solution database, where you store all of your past experiences and being able to sample from it and learn from your past experiences to improve your next iteration generation. So this can be any sort of like ideas, guidance, or reflections over what have you built so far. So basically, this is the entire loop of the framework. And running this API is also pretty simple. You can either provide some sort of like evaluator over your problems, and maybe you have some initial program of like showing that, okay, here's like a simple example of how you can run this program. And then you can run with support a wide range of algorithms, like for example, JEPA, OpenEvolve, Shinkai Evolve, and also 2 to 3 adaptive algorithms that we'll talk about next. So
hello. So on top of the SkyDiscover framework that Shu talked about, we implemented 2 algorithms to show that the previously supported algorithms like OpenEvolve, JEPA, and Shinkai, albeit being really good, can be dramatically improved if we can separate different components cleanly in the SkyDiscover way. And for the first algorithm, we asked the question, how can we design a search strategy that adapts based on the progress of evolution? And we introduced Agarwal, ADA standing for adaptive evolution. And it adapts in 3 different levels of granularity, local adaptation, global adaptation, and meta-level guidance. To go over them briefly, local adaptation asks the question, given a population of different candidates programs, which parent we should sample, and then it does exploration and exploitation adaptively. A global adaptation asks this question, okay, in order to introduce diversity to our population of programs, we are going to partition our programs into subpopulations that we call islands, and also island-based evolution is something that existed in the evolutionary search genetic algorithms since 1970s, 60s. But now having different islands, how do we create new islands? It is created adaptively and dynamically at Agarwal, the new islands. And also having multiple islands, the new islands are chosen based on upper confidence bound score, so it's a multi-rank banded problem. And lastly, meta guidance, what it does is it adapts the solution tactics that guide the search process. The motivation from Agarwal obviously came from adaptive subgradient algorithms like ADAGRAD or ADAM, because if this was a continuous optimization problem, this is almost a solved problem. You look at the history of gradient updates and first moments of your or second moments of your gradients, and have tunable learning rates for different parameters. But this is essentially the zeroth order optimization problem. So yeah, the main thing Agarwal tries to answer is how do we create adaptive primitives for this zeroth order optimization problem. And how it maps to SkyDiscover is we build local and global adaptation in solution selector and the solution techniques in the context builder. Now my friend is going to explore EvoX.
Hey, so given that we had this algorithm of ADA evolve, which was more about adaptively doing search for doing evolution. So we also came up with another idea where all we wanted to do was that how can AI basically try to change the scaffold of sampling itself. So AI is going to optimize its own optimization loop. So you can think about it more like in the meta learning kind of fields where you try to learn the way to learn itself. So in this one, what we do is we basically have the inner loop of solution generation, but with the solution generation, the sampling algorithm and the way you are presenting the solutions to the model also gets evolved as the iterations happen. So when the inner loop basically stagnates, if it is not performing well for a window of iteration, the outer loop is going to take the feedback of what it did and also manages the search algorithms that were used in the past and tries to come up with a newer search algorithm. So to show this, I'll just try to go over this example where you try the task of signal processing, where you start with a random algorithm, but as soon as it starts stagnating, you basically try to see if there is any new sampling algorithm that can help. Now, in this case, the model comes up with a technique where it starts using multiple objective sampling, where because the signal processing task basically requires you to optimize for multiple matrix at the same time. So the algorithm switches to a mode where it tries to sample candidates which are best in different aspects and uses them together to guide the algorithm to guide the downstream LM to do better in the task. And yeah, that is how we get this bump because of the newer algorithm. So just quickly sharing some results for time. So of course, we tried a lot of these systems problems. So ADRS is another work that we did in the past, in the summer, where we tried coming up with several system challenges which are published in different venues. And we asked an LLM to see if it is able to come up with a new heuristic which can do better. So we compared this one with all the human SOTA, which is the published numbers, and all the open source frameworks across two models. And both the algorithms, ADA Evolve and EvoX, were able to beat all the open source frameworks out there across the two models. And then we tried all the Alpha Evolve math problems where it starts from circle packing to several of the tasks, and signal processing is the one that I was showing in the case study. And again, we can see that for many of the problems, uh, both for GPT-5 and Gemini 3, we are able to beat all the open source frameworks almost always. And also we are able to match or beat Alpha Evolve closed source numbers that Google presented in their work. Yeah, and these are some other challenges which are frontier CS, which are like competitive programming challenges. So in this also we compared against the open source frameworks, and both Ada Evolve and EvoX were able to beat the open source ones. Now, one quick thing that we also wanted to see was how do these two algorithms fit. So, of course, because we know that Ada Evolve is more like a sophisticated search, so it gives you a very good start. So that is how it works well. And EvoX is something that is more about learning from feedback, so it takes somewhat more iteration to scale better. But one thing that we found pretty exciting was that if you start with Ada Evolve and then you let EvoX evolve in on top of Ada Evolve, it can beat the performance of both of them individually. So they are pretty much complementary in that aspect. Yeah. So yeah, that is almost all of our talk. So the key problems that, of course, we are trying to see now is that what are the harder problems to use these tools next. And yeah, we will be excited to know more about what are the problems people are trying to solve. And yeah, this is our blog post and code base. Would love to have comments and shares for them. Thank you.
Any questions for the SkyDiscover team?
Thanks for the talk. Just for your comparisons against other evolutionary systems, how do you make sure that you're comparing like apples to apples in terms of like the same compute cost, things like that?
Yeah. So sorry. Never mind. Yeah. So the way we compared it was mainly so of course there is this question of how we compare against them in terms of budget. So for the results that we presented, we tried capping all of them to the same number of LLM calls. So that is how we kept the budget same. But of course, there is also this point of token cost. So in the paper, we present the result where we are also showing the scaling of these techniques in the cost and quality aspect, where we show that EvoX and Ada Evolve can quickly ramp up the performance and within like $2 to $3, whereas the same performance it takes probably like tens of dollars for even Cloud Code to achieve to that number. So that is the axis that we try to compare against.
And then maybe also, do you see like a big role of having a human expert in the loop during this process, or yeah, do you think it's
Yeah.
full LLM?
Yeah, good question. So Yeah, we definitely see that. Of course, it becomes a bottleneck when you have humans. So it is almost automated for us now. But we also support in SkyDiscover two things which are pretty exciting. So of course, we have a very clean dashboard where you can monitor the entire evolution, and there is like a very easy way for a human to intervene, trying to give any kind of feedback as well as trying to pick a given parent if the human feels that this should be a direction to follow. And again, to keep the human more lighter, we also have Claude Code in the loop. So it can be like Claude Code sits on the UI, and Claude Code can guide the evolutionary process. And in that way, human can be sitting even on behind of Claude Code, trying to do the entire evolution for any hard problem.
And did you guys have any expert, like an example of an expert in the loop, or you didn't try it?
So again, some of these problems are not very hard to do. They can be done pretty easily with LLMs, but we are trying some harder challenges where we are trying to build like systems from scratch and things like that, which are more ill-defined, and there are more hacking behaviors that come up. So in that, we generally use these tools that we have where the human is having this UI or the interface of Claude Code, and the evolution happens in the background, and the human and the Claude Code can basically intervene whenever they see some hacking behavior. And in that way, it basically doesn't let the agent do things which are very, very hacky, as well as it tries to give you the right feedback whenever the model gets stuck in some sort of local minima.
Nice, thanks.